Welcome to Spring LIB.
Here we have a kind of a compound capacitor where we have between the two conducting plates here we have two different dielectric materials, and they each take up half of the distance between here, and then they also have the same cross-sectional area. So the total cross-sectional area is 7.989 centimeters squared. The total distance between these plates is 4.62 millimeters. The one material has a dielectric constant of 11, and the other one has a dielectric constant of 12. So what we can do here is we can think about these as two capacitors in series. Okay, so this capacitor, it's like we have, if we this would be the equivalent system of if we pulled these two things apart and put plates on here, right? So we had this capacitor, and then down here we had another capacitor, and so this would have D over 2, this would have D over 2, because we're going to basically there's going to be some charge stored in this gap, in this interface here. So this is basically two capacitors in series. So we know the two capacitors in series, the total capacitance is C1 times C2 all over C1 plus C2. And now we can get the capacitance in terms of the geometry and the dielectric constant and stuff. So that's the first capacitor has a capacitance kappa 1 epsilon naught A divided by D over 2. And the second one has a capacitance kappa 2 epsilon naught A divided by D over 2. So we can see that basically we could factor out this, I factored out a capital K here, and that just call it that, right? So everything in this is all the same in both cases. And so really all we're going to do is plug these things into here and do a little algebra, and we wind up with the equivalent capacitance is kappa 1 times kappa 2 all over kappa 1 plus kappa 2. So that makes sense because it looks a lot like that. And then we have our constant out here, 2 epsilon naught A divided by D, and that's actually this K value. So it's not, shouldn't be a surprise that these dielectric constants kind of combine just like the capacitances do. And so we can see that if things go, if either one has a dielectric constant of 0, well then we have a capacitance of 0, and so then things basically we have a short. Let's see here. Say one gets very large compared to the other, then that would go away, right, compared to this, and then that would cancel that. And so we just have the total capacitance would be dominated by the smaller one, which makes sense. So anyway, we have all of the values that we can plug in here, and obviously we just need to make sure we do some unit conversions on everything here to make sure the units work out. But in the end, we get 1.73 times 10 to the minus 11th farad, or 17.3 picofarad is the capacitance of this composite capacitor.